welcome back. Your dreams were your ticket out. Welcome back to that same old place that you laughed about. Well, the names have all changed since you hung around, but those dreams have remained and they've turned around. Who'd have thought they'd lead you? Who'd have thought they'd lead you? Back here where we need you. Back here where we need you. Yeah, we tease him a lot, 'cause we got him on the spot. Welcome back. Welcome back, welcome back, welcome back. Welcome back, welcome back, welcome back. We always could spot a friend. Welcome back. And I smile when I think how you must have been. And I know what a scene you were learning in.
Jarvis, you there?
At your service, sir.
Good morning, chemistry honors. Superhero week continues. As you can see, Iron Man lab, Tony Stark's lab, basically what we're looking at. And you can see I have a bit of a froggy throat and a face for radio. So let's go right into what we're doing today. It's 9.01 classification of matter, and this is mostly knowledge based. So let's do some definitions here about what's what, and use your notes on this. So let's get into it. So continuing, we have classification of matter 9.1. Here on Earth, matter is usually classified as solid, liquid, or gas. Ask someone what causes matter to turn from a liquid to a solid, and they will most likely answer because it gets cold and a liquid freezes. Well, temperature has a strong influence on changes in states of matter. It's really about the energy. Consider this cube we have here. If you were to see this metal cube sitting under the counter, you would automatically think it was frozen. Okay, so what is the difference between a cube of metal and a cube of ice? Well, they're both solid cubes, but they can become solid at different temperatures. They also become liquid at different temperatures, of course. You have the liquid gas phase change, solid liquid gas phase change graphs so that you can do, and we have done since you were freshmen. So let's look at this as far as the questions you'll have to answer. All right. So at room temperature, steel is a solid. What is a liquid? And carbon dioxide is a gas at room temperature. Why is that? Why are they not all solids at room temperature? And why are they not all liquids at room temperature? In this lesson, you'll identify properties of solids, liquids, gases, compare states of matter with respect to kinetic energy, and apply factors that increase rates of diffusion of gas through things and moving and stuff like that. So let's get to it again, to the next slide. Okay, so in our first slide here, we have an image of a Creative Commons public domain dedication license, so that is okay to have. We don't see icicles in South Carolina. We do see them from time to time. Where I'm from in Michigan, we see them all the time. The image that consists of a solid, it's an icicle, it's frozen water, of course, liquid dripping water and gas, water vapor in the atmosphere, simultaneously at the same temperature and pressure. How can this be? So they exist all together. They have a solid, this here, and it has a liquid of dripping water, and it also has gas and water vapor in the atmosphere. And they all occur at the same time. Well, how can that happen? It's all about energy, and let's discuss the properties of solids, liquids, and gases before we discuss under what circumstances they exist. Alright, so you have a solid is rigid, fixed shape, fixed volume. You have to know that in your questions. Liquid, not rigid, no fixed shape, and a fixed volume. That's just, it's basically not going to change in volume as far as what it can contain or be contained by. And this is, of course, not rigid as well. No fixed shape and no fixed volume. So you do have to maybe do a Venn diagram to help you learn that a little better. So let's talk about liquids. Generally, the atoms in liquids have more kinetic energy. Okay, so they move around more. They have more energy. The atoms than a liquid than a solid is, of course, moving around more. Forces between the molecules. There's the kind of the concept besides chemistry, or besides temperature. The forces between the atoms hold them together, but not as strongly as forces hold molecules in solids. Therefore, molecules in a liquid, although loosely held together, slide past one another, allowing liquids to take the shape of their containers and run. And there's viscosity issues and things like that. Try to describe the shape of this liquid. Basically, it's the shape of the beaker. Okay, if you pour the liquid from the beaker into any one of these containers below, that would happen to the new. What would happen to the new shape of the liquid? Well, they take the form of its container. But the volume remains the same. You still have what looks to be about 50 milliliters, if that's the measurement they use, in that container. It's not important that we describe the shape of the liquid, as the shape can change. We can describe the volume of the liquid, whether it is poured into the decanter, the glass, or the vase, as some say. The liquid will have a volume of 49 milliliters, or 0.049 liters, and I did get that wrong because I can't see that. That's an estimated guess by my look at that. My eyes aren't that good. So if you said 50 milliliters, I wouldn't say, oh, that's way off. It's a vision issue, it's an error on that one. Not a parallax error, but an error. And I should be chastised severely and taking that in consideration. So, next slide. So let's look at gases. Gases in our subtropic environment. Water vapor makes up about 2 to 4% of the gases we breathe in. The most abundant gas is nitrogen. As some might think it should be oxygen, but it's followed by oxygen. 76% nitrogen, 19% oxygen, and argon is there, with carbon dioxide following. Okay, the rest are trace amounts of neon, helium, methane, krypton. All right, and those things you can read here. You've heard of ozone, I've hoped in the past. Other than the water vapor, which varies on less humid days, the composition of gases in the atmosphere is fairly uniform or homogeneous. Or homogeneous, if you want to pronounce it that way, depending on which country. This is basic because gases tend to expand to fill their available space. This volume is called diffusion. So you spray perfume in a corner, it's going to diffuse about the room. Of course, spread very widely depending on how big the room is. So let's take a look at this video.
Why smells spread. Before we
Let's
start,
try that again.
you need to recall in this lesson, we are going to learn about diffusion of gases. This will help you to understand how gases behave and also explain why smells spread. Before we start, you need to recall what solids, liquids and gases are like in terms of their particles. In particular, I'd like you to ask yourself, how are the particles arranged in a gas? Pause the video and restart it when you think you have the answer. The answer is the particles in a gas are spaced out and move about very quickly in random directions. Did you get it right? This, of course, explains why a gas takes the shape of its container. It's because the particles will each continue to travel in a straight line until they hit something, in this case the wall of the container. So, the smelly gases given off by rotting vegetables in a sealed box will fill the box with rotting vegetable smell, but you won't be able to smell them outside the box. However, take the lid off the box and those particles will no longer bounce off the lid and be contained. They will start to escape into the air around the box. You'll soon notice the effect and will be able to smell the rotting vegetables. and that's those gas particles reaching your nose by diffusion. Diffusion is the random movement of one gas through another, from a region of high concentration, in this case inside the box, to a region of low concentration, in this case outside the box. It is a process that doesn't rely on wind or air currents. It will happen even if you are inside a building and the air is completely still. Now, there are many examples of diffusion, but smell is probably the most obvious one. These could be food smells, body smells from other people, the scent that a plant gives off to attract pollinating insects. And the same even applies with the smoke from a candle after it has been extinguished. It spreads out, and it's all due to diffusion. Now, here's a challenge for you. If someone walks into a room with some fresh flowers, why does it take a while for the smell of the flowers to fill the room? Why can't you smell them straight away? Pause the video, have a think, and restart it when you think you have the answer. Well, just as the gas particles can hit the walls of a container and rebound, the particles can also hit each other. It doesn't matter if there is only a single gas or a mixture of gases. These collisions between particles are always taking place. It's very similar to trying to walk in a straight line through a busy crowd of people or a marketplace. It's very difficult to do without bumping shoulders with someone and changing direction. This explains why it takes a while for a smell to get from one part of a room to another. The high concentration of gas or smell particles takes time to spread out due to the collisions with the other gas particles in the air. And that is diffusion.
Okay, great stuff, great stuff. Of course, the gases have enough kinetic energy to overcome forces of attraction between particles. So gas particles will diffuse to fill the available space, as we talked about before, but not all gases diffuse at the same rate. So there's diffusion rates. Okay, size. Small particles diffuse faster than larger particles. Aerodynamic, maybe. Temperature. Increasing temperature increases the rate of diffusion. More movement, more energy being absorbed. Concentration. The higher concentration of the gas, the faster the rate of diffusion. It's almost like an osmotic concept. It's like cell membrane rate of diffusion. Okay, that is rather pungent. All right. Might get to your nose quicker. Gases have no fixed shape or volume as they will expand to fill the container. You can predict which gas diffuses faster, hydrogen, chloride, or ammonia. Okay, so look at that one. Gases have no fixed shape or volume. Can you predict which gases diffuses faster based on these types of things? I give you a hint. Calculate the molar masses of each gas. There you go. That's one hint. Size. Concentrate. Determine which will diffuse faster rate, then watch the video to see if you're right. Make your guesses now.
In this diffusion experiment, we're looking at the diffusion of HCl gas and ammonia gas. We have concentrated solutions of HCl and ammonia on the cotton in the tube. The HCl and the ammonia escape from the solution. The gas travels down the tube. The rate at which the gas travels down the tube is dependent upon the molar mass of the gases. When the gases come together, they react to form solid ammonium chloride, which forms a white solid in the tube. We see that the white solid is closer to the HCl side than the ammonia side. This is because the ammonia has a lower molar mass and diffuses faster than the HCl.
Okay, so moving on to the next slide, guys. Keep up, and we'll get you to the next place. So we're going to talk about the next slide here, and that's gonna we had those. Now plasmas. Okay, we're going to fade back in here. Plasmas, a gas. It is a gas. Okay, but it changed electrically charged particles. Contains. Let's go. Good day for this. Is a fourth state of matter that exists naturally in stars, but can be made artificially or by lightning strikes here on Earth. When lightning strikes, or when we apply the large amount of heat or electrical, energy, flow of electrons, maybe. Okay, the surrounding gases are in the air are ionized. They are stripped of outer electrons, leaving negatively charged free electrons and positively charged parent atom molecules. Because of the unique composition of charged particles, plasmas can conduct electricity and respond to magnetic fields. See how that kind of looks? I know it's not lightning. It doesn't occur in the same format or have the same mechanism, but you can see here there's probably a positive or negatively charged surface, and it goes towards that. Although we can artificially create plasma in plasma lamps and plasma televisions, naturally occurring plasma can be found in stars like our sun and in the auroras. The northern hemisphere has a lot of those auroras where I'm from, actually more north than I'm from. Northern and southern lights actually exist. Watch as Dr. Lucy Green of the University of Central London's Department of Space and Climate Physics discusses her research into plasma and the sun.
One of the things that interests me about the sun in particular is the fact that it is this hot, dense plasma sitting in the cold vacuum of space.
Plasma is often referred to as the fourth state of matter. So if you have a solid, you can heat the solid and turn it into a liquid. So first to second. If you heat the liquid, you can turn it into a gas, the third state. But if you keep heating your gas, you can actually rip apart the atoms that make up the gas, and you can tear the electrons from the atoms. And then you end up with a plasma, which means you have a soup of positively and negatively charged particles.
I think that plasma still invokes some sense of mystery when you hear that word, and that maybe we think it is some kind of exotic and uncommon substance. And what we want to do this evening is show you that actually it's a very interesting and a very abundant substance.
As a space scientist, I'm extremely interested in plasma because 99% of the known universe is in a plasma state. I mean, most people in their day-to-day lives don't necessarily experience a plasma. Maybe they're familiar with it because we have so many plasma TVs now, but as a space scientist, it's absolutely fundamental to understanding the universe.
We're looking at the plasma here, which has a temperature of about 80,000 Kelvin, 80,000 degrees centigrade. So incredibly hot gases. And it's actually helium which is giving off the light at this temperature. If you heat helium enough, you can make it shine in the ultraviolet light.
I study our local plasma sphere, the sun. So the sun's outer atmosphere is a very hot plasma, and it actually is a very interesting physical place to study, and it is also something that really does directly impact us here on the Earth as well.
Okay, so we're going to look at, I think we have about 3 more slides to go. We're going to look at that now. So, your first question's another video, States of Matter Review. So, guess what? You took notes on it, or hopefully, and now we're going to get another review on the information you just saw. So, should I play this and put more time on this video? Well, there's 4 minutes, and I'm going to let you go ahead and do that yourself, because, this is just one of those things that you have to do independently, and I appreciate all the questions in the office hours this week so far. So, again, this is 9.1, your classification of matter, so I'm going to jump right ahead. We got informational, good. So we got one more. I don't go over questions, but you can come on and ask what you did wrong and how to fix them. because we do have a, remember, and a market period's coming up. Let's get on this. So now let's go. I won't waste your time. Lesson summary. You know, you had solids have fixed volumes and fixed shapes. Of course, they, you know, mostly they still are moving technically in atoms, but liquids have fixed volumes but not fixed shapes. Gases have neither fixed nor volumes nor fixed shapes. Like a gas, plasma lacks a fixed volume and shape. But unlike a gas, it conducts electricity, basically movement of electrons from positive to negative flow or opposite. They respond to magnetism. The state of matter depends on the kinetic energy of the particles matter. And of course, the next sections that are coming up in other presentations are going to have how more we can break down the definition with different forces, temperatures, and things like that. So great job today so far. Let's close this out by seeing what's coming up. So what is coming up on Tony Stark's little lab later here? Well, we got tomorrow, of course. Let's get this down low. There we go. So, having said that, we're going to look at tomorrow. We have 9.1 and 9.2 and 9.3 and 9.4 due by the end of the week. And we'll get through this unit together by watching this video or other videos that I put out later this week. Remember, Superhero Week. Have a great time doing what you need to do. Iron Man Day, kind of. All right, so Tuesday, November 2nd, signing off. And remember, you can be a hero